Okay, so now it's time to do some exercises. V a real Banach space and assume that the parallelogram law holds. That means for every xy in V, we have norm of x plus y by 2 square plus norm of x minus y by 2 square is 1/2 of norm x square plus norm y square. Then V is a Hilbert space. So this is the real version of the Frechet-von Neumann-Jordan theorem, which says that if you have the parallelogram law, then the norm must come from a inner product. So we have to define the inner product, and then so we work backwards actually and try to get a formula for the inner product in terms of the norm. So one of them, so if you are in the real case, then this will be 1/4 norm of u plus v square minus norm of u minus v square. So define. So you define this inner product. So we have to check that this is the, so to show this is an inner product which generates the norm. So generates the norm is very easy, because if you take UU, so that's equal to 1/4 of norm u plus v, u plus u is 2u, so you get 4 norm u square. This is 0, so that's equal to norm u square. So it certainly generates the norm, there's no problem with that. And also it's easy to see that uv equal to vu. Okay, that's obvious from the definition, obvious. So we now have to show linearity. So need to prove linearity. So we do that in 2 stages, so or several stages. Let us take first 2uv. So by definition, this is 1/4 of norm 2u plus v whole square minus norm 2u minus v whole square. Okay, so that's equal to, I am going to write this as 1/4 as norm u plus v, in fact by 2 whole square, so that I will remove the 1/4 from here, minus norm, so this is the whole, norm is for the whole thing, norm u plus u minus v by 2 whole square. So now we are in a position to use the parallelogram law, and therefore that's equal to 1/2 of norm u square plus 1/2 norm u plus v whole square minus the difference between the u minus v is just v, so you have norm v by 2, norm v squared by 4. Similarly for the other term, so we will write that, so minus 1/2 norm u square minus 1/2 of norm u minus v whole square minus norm v square by 4. And therefore this 2 cancel out, these 2 cancel out, and this is equal to, and this by definition is nothing but 2 times uv. Okay, so 2uv equals 2 times uv. So now, so that is one relationship. Now what about u1 plus u2v? So that's equal to 1/4 of norm u1 plus u2 plus v whole square minus norm of u1 plus u2 minus v whole square. So I am going to write this as u1 plus v by 2 plus u2 plus v by 2. Okay, so let us write this as so this will give you the by 4 will be taken inside. So from the parallelogram law, this will be equal to norm of u1 plus 1 half of that v by 2 whole square plus 1 half norm u2 plus v by 2 whole square, then minus the difference of it, that is 1/4. So u1 plus v by 2 minus u2 plus v is norm u1 minus u2 whole square. Okay, so then similarly minus 1 half of norm u1 plus v by minus v by 2 whole square minus 1 half norm u2 minus v by 2 whole square minus 1/4 norm u1 minus u2 square. Again these two get cancelled out, and if you look at the first two terms and the next two terms, this is nothing but 2 times u1 v by 2 plus 2 times u2 v by 2. But you just saw that 2uv is 2u times v and uv is a symmetric form, so that's equal to u1v plus u2v. So u1 plus u2v is u1v plus u2v. Now we have to show that alpha times u of v is alpha uv. That is what we have to show. We have shown it for 2. Now if you have 3uv for instance, this is equal to 2uv plus uv, which is 2 times uv plus uv, which is 3 times uv. So now if you take any integer m, so by induction m times uv equals muv. And also you have that u of minus v. If I put minus v in the definition, so let me write it here itself, u of minus v is equal to minus of uv from this definition, because this will become plus and this will become minus, and so that is just minus of uv. So that also we have. We already have this, and therefore these two implies m times uv equals mu times v for all m in z, all integers. Okay, so then n times m by n uv equals mu times v equals m times uv, and therefore m by n uv equals m by n times uv. So it's true for all rationals. Now therefore true for all reals by continuity. The inner product is obviously, norm is continuous, therefore the inner product which we define is also continuous with respect to and therefore if you take any real number approximated by rational numbers, and therefore you have this, and therefore it's true for all. So we have that norm of u1 plus inner product u1 plus u2v is u1v plus u2v. It is symmetric, and for all reals lambda we have lambda uv equals lambda uv for all lambda in R. So it satisfies all the properties of an inner product, and therefore the norm is generated by an inner product, and therefore we have that it comes from that it becomes a Hilbert space. Now in the complex case, so V Banach over C, okay, parallelogram law holds, then implies V is Hilbert. That means the norm comes from an inner product. So we again solution. Now you define the inner product in the following way. So uv equals 1/4 of norm u plus v square minus norm u minus v square plus I times norm u plus iv square minus I times norm u minus iv square. So it's very similar to the real one. So if you take this is the real part, this imaginary part also looks very much like the real one, real part. So okay, so this, if you now take uu, then you get 1/4 of 4 norm u square, second term will be 0, and then if you take u equals v, then 1 plus I will come out, mod of 1 plus I is root 2, so plus I root 2 times norm u square minus 1 minus I also has root 2 has the modulus, so minus I root 2 norm u square, and therefore that gets cancelled, and therefore you get norm u square. Okay, now I will let you to check vu equals uv bar. So it is just a straightforward computation. You just have to pull out the i's and so on, and there is no such thing. Okay, now by 1, see this part and this part, but for the I, this part and these two parts looks exactly like what we did in the real case, and therefore you have that u1 plus u2 v equals u1v plus u2v. Okay, so you can the linearity. So now we only also you have that lambda u times v will be equal to lambda times uv for all lambda real, because again this inner product looks exactly like the previous case, and therefore we can repeat all those arguments, and then and now you just take iu times v, apply it to the definition, and then you can, so this is I times uv. So check. So this also check. So these are just straightforward algebraic manipulations, and therefore you have that for all complex constants you have lambda uv equals lambda times uv, and therefore you have linearity in the first variable, and you have conjugacy, and you have that the norm is produced, and therefore this becomes a Hilbert space. Okay. H a Hilbert space, M contained in H closed subspace, and P orthogonal projection onto M. Then this implies that norm P equal to 1. Okay. So solution. So it's an orthogonal projection. So x can be written as px plus I minus px, and you have that px is orthogonal to I minus px because it's an orthogonal projection, and therefore norm x square equals norm px square plus norm I minus px square. This is the cross term will not exist. This is in other words a version of the Pythagoras theorem. Okay, so you have that norm px is less than or equal to norm x, and therefore norm p is less than or equal to 1. Now you can do the other thing very easily. If x is in M, then you have px equals x, and therefore this implies that norm p equal to 1. Another way is to show that since it's a projection, you have p square equal to p, therefore norm p is less than or equal to norm p square, and therefore this implies that norm p is bigger than or equal to 1, and therefore that also gives you the opposite inequality, and therefore you have norm p equal to 1. So you can do it in either of these two ways. Okay. Four. This I already mentioned in the class but didn't do it fully. I asked you to verify it. So let H be a Hilbert space, and P in L of H such that P equals P square equals P star, then P is an orthogonal projection. So we have to show that M equals range of P, and to show M perp is the range of I minus P. Okay, so that will show that it is an orthogonal projection. Okay, so let us take PZ, which is in M, so this belongs to M, and this belongs, and X minus Px. So this belongs to range of I minus P, and see what the inner product is. So this is equal to Pz X minus Pz Px. So that's equal to Pz X minus P star Pz X, and P star P is equal to P square because P star equals P, and that's equal to P again. So that's equal to Pz X minus Pz X, which is equal to 0. So this implies that range of I minus P is contained in M perp. Okay. So now you can complete the proof in many ways. So let me do one of them. So let us take, we have to show that it's equal. So let me take the Han-Banach method. So let Y belong to M perp. Okay. Such that Y Z minus Pz equal to 0 for all Z in H. That means it vanishes on range of I minus P. Then I want to show that it vanishes everywhere, and therefore okay, I think we won't do this because that will only show it is dense, but it won't show that it is in fact equal. Okay, so let us do another way. So we have that if X belongs to range of P intersection range of I minus P. Now range of I minus P is orthogonal to this, and therefore you have x equals 0 implies X is equal to 0. So range of P and intersection range of I minus P is 0. Okay, and then any X can be written as Px plus I minus Px, and therefore this is in range of P and this is in range of I minus P, and therefore you have H is equal to range of P direct sum range of I minus P, and H is also equal to range of P, which is equal to M for us, direct sum M perp. Okay, and therefore, and you have range of I minus P is contained in M perp, and therefore this implies that range of I minus P equals M perp. Okay, so that completes the proof. Okay, so that is then 5. Let us take H equals ln2. We call this is equal to Rn with the norm 2. Okay, and then you look at the matrix J equals J of ik, where J of ik equals 1 by n for all 1 less than equal to ik less than equal to n. So that means it's 1 by n, 1 by n, 1 by n, 1 by n, and then 1 by n, 1 by n, 1 by n. So okay, so it's a matrix which all same entry everywhere. Show that norm J equals norm of I minus J equal to 1, because where j is now, so j takes ln2, so since that is j takes ln2 to ln2, so it's a linear mapping, and therefore it has a norm. We want to show that now. Okay, solution. So by inspection we have j equals j star, the adjoint is the same, and that's equal to j square also. So if you multiply j by j, you will get, once again you will get j again. So this is implies j is an orthogonal projection, and therefore norm j equals 1, and that's also equal to, similarly I minus j is also an orthogonal projection, because if P is an orthogonal projection, I minus P is an orthogonal projection, and therefore that's equal to norm I minus j. Okay, so that is simply done. Okay, so let H be a Hilbert space and U in LH unitary. Then norm Ux equals norm X for all X and H. That is, it's an isometry. We have already seen this. So you have U star equals U star U equals identity, and therefore you have norm X square equal to U star U X X, which is equal to Ux Ux, which is equal to norm Ux square, and therefore you get this. So this we have already seen in the previous lecture, where we computed the spectrum of a unitary operator. Okay, so A 7A H Hilbert space, W contained in H closed subspace, A H cross H to R continuous H elliptic bilinear form, and F is given to H. Then there exists a unique W in W such that AWV equals FV for every V in W. So we proved this, I mentioned this as a remark, we proved this, the Lax-Milgram lemma, for the whole of H, and now we are saying that is true even in a solution. So A W cross W to R is also continuous for the same, because it's continuous on H, and W elliptic as well. If it's H elliptic, it's also W elliptic, because that's only a subspace. Now if you took FV, this is equal to PFV for every V in W, where P from H to W is the orthogonal projection. So by Lax-Milgram, because W is a Hilbert space in its own right, there exists unique W in W such that AWV equals PFV for every V in W, and this is nothing but FV. Okay, and therefore we have shown that there exists a unique solution. B, norm of W, the solution, is less than or equal to norm F by alpha. So norm W square is less than alpha times this is less than AWW, that is the ellipticity condition, and this is equal to FW because it solves the equation, which is by Cauchy-Schwarz less than or equal to norm F times norm W, and therefore this shows that norm W is less than or equal to norm F by alpha. So you see that this estimate is independent of the subspace. So whatever may be the subspace where you are solving this problem, the solution has the same estimate for the norm. Okay, so this is the thing. Now C, let U in H be the unique solution of AUV equals FV for every V in H. So you take the full problem of the entire space. Then norm of U minus W is less than or equal to M over alpha times infimum of norm U minus V, V in W. Okay, so solution. So alpha times norm U minus W square is less than or equal to A of U minus W, U minus W. I am going to subtract and add something. So U minus W, U minus V plus V minus W for all V in W. It's for all V anyway. I am going to do it for that. This is equal to A of U minus W, U minus V plus A of U minus W, V minus W. Now what is this? Belongs to W, remember. So AU V minus W is F of V minus W because U is the solution in the whole space, and AW V minus W is F of V minus W because its solution is in the subspace. So both of these are the same, so this term becomes 0, and this is the thing to M times norm U minus W times norm U minus V. Okay, therefore for every V in W you have norm U minus alpha W whole square is the same to M by alpha times U minus V. And therefore I can take, this is true for all V in W, so this implies norm U minus W square is less than or equal to M by alpha infimum of V in W norm U minus V. Okay. D, H separable and En n equals 1 to infinity orthonormal basis. Wn equals span of E1 to En for each n. So that's a finite dimensional closed subspace. So F is given in H. So Un in Wn such that A of Un V equals Fv for every V in Wn. Then Wn converges to U. What is U? U is the solution in the whole space. AUV equals, so this tells you that you have, so these solutions are approximations of the original solution. Okay, so let us take Un tilde. Un tilde equals sigma I equals 1 to n U ei ei. Then what do you know by Parseval or from the theorem? Because Un is an orthonormal basis, you have Un tilde converges to U in H. Okay, this is what we know because that's Un. U is nothing but the infinite series associated to this, and therefore you have norm of U minus Un is lesser, and Un tilde belongs to Wn. Okay, so norm of u minus w by the previous thing is less than or equal to m by alpha. Infimum of norm of u minus v for any v, I am going to take v equals un tilde. So this is less than u minus un tilde, and that goes to 0. Therefore, norm of u minus un goes to 0. In fact, remark, we can even prove the Lax-Milgram lemma directly without from this fact, without using. So we can prove the existence of un directly, and therefore you can prove Lax-Milgram lemma also. How? So if I want to existence of un without Lax-Milgram. So you want to find un such that un v equals fv. So it's by linearity, it's enough to check it for the basis element. So you take a un en ei equals f ei for 1 less than or equal to I less than or equal to n. Then un itself can be written as sigma alpha I ei, I equals 1 to n, and you substitute that here. So you get sigma j, let me put j equals 1 to n, a of ej ei alpha j equals fei 1 less than or equal to I less than or equal to n. And therefore you get a linear system a alpha equals f, where a, the matrix equals aij, and aij is nothing but a of ej ei. Okay, and alpha is the unknown vector, which is alpha 1 to alpha n, and capital F is the given vector, which is fe1 fen. So if you solve this linear system, you will get the alphas, so you will get un, and that will prove. So all you need to show is that this matrix A is invertible, which it is, because if you take any x1, x2, xn, x transpose equals this, so then x transpose ax is nothing but a of sigma xi alpha I sigma xj alpha j, xj alpha j, sorry, not alpha j, ej xi ei, and therefore this is greater than or equal to alpha times norm sigma xj ej square, and that's equal to sigma alpha times mod x square. Mod x square is sigma xi mod xi square. Okay, that is the, since the ej's are orthonormal, and therefore this matrix is positive definite, and therefore A is positive definite, implies 1 1 implies invertible, and therefore there exists a unique solution alpha, implies there exists unique un solution. And now, because you know un converges to u, you can also now prove the Lax-Milgram lemma. You have a unv equals fv for every v in wn. So given any v in h, you have v, write vn equals sigma I equals 1 to n v ei ei, and therefore vn converges to v in h, and therefore you have a un vn equals fvn, and now pass to the limit, because a is a continuous Bain linear form. This gives you un goes to u and vn goes to v, and therefore this gives you fv, and therefore we have produced a solution for the original for every v in h. Okay, so therefore we have proved Lax-Milgram lemma by this approximation process, at least for the separable Hilbert space. So we will continue the exercises.